Hi, my name is Janani and I'm a petroleum engineering student.
Hi, my name is Misha and I'm a chemical engineering student.
Hi, my name is Sri and I am a petroleum engineering student. Imagine this. You're at a home on a quiet afternoon. The sky is clear, the neighborhood is calm, and nothing seems unusual. But then, the very air around you changes. You cannot see it, you cannot smell it, and you cannot feel it. Then within minutes, you are gasping for air. This is not fiction. This is what happened in Sulphur, Louisiana on April 3rd, 2024, when a carbon dioxide pipeline incident released thousands of barrels of CO2 into the atmosphere. This video is a deep dive into the ExxonMobil Denbury CO2 pipeline leaks. Before we dissect the situation in detail, let us take you through the timeline of events of what actually happened in Sulphur.
At 6:18 p.m., the hazard presented itself. A high-pressure pipeline carrying supercritical carbon dioxide ruptured at ExxonMobil's power station in Sulphur. The system had already deviated from the safety. A sudden pressure drop signaled that something was wrong. Normally, this will trigger the alarms and automatic shut-off valves. But on this day, the monitoring systems were offline and no operator was present to respond. The warning went unanswered. It was not until 8:20 p.m. that an ExxonMobil operator arrived on site, almost 2 hours after the leak was reported.
By then, the lost event was fully underway. Around 31,000 barrels of carbon dioxide had escaped into the atmosphere. For nearly an hour, the gas vented unchecked, forming a cloud that was odorless, colorless, and potentially deadly. Anyone exposed risked dizziness, suffocation, or even worse. The impact was felt. Emergency services were alerted not by Exxon systems, but by a passerby. Residents within a quarter-mile radius were told to shelter in place. Fortunately, weather conditions dispersed the plume before it caused serious harm.
Having covered the what, we turn to the why. 2 root causes stand out: material degradation in carbon dioxide CO2 pipelines and gaps in process control and protective layers. Firstly, one of the most commonly agreed upon root causes of the CO2 pipeline leak is the degradation of pipelines due to transported media. Why is that? Research by Bielka et al. 2024 shows that even the smallest amounts of water in a CO2 stream can form carbonic acid H2CO3, accelerating internal corrosion and pitching and accumulating at weld toes, elbows, and dead legs. A sudden release of this acid drives rapid decompression and deep chilling, which can embrittle seals and shrink elastomers, and ruins the pipeline integrity. In particular, O-rings, which are mechanical gaskets that are commonly used in sealing, can absorb CO2 under pressure and then suffer rapid gas decompression on pressure collapse, causing blistering, cracking, or extrusion on the pipes.
Secondly, deficiencies in process control and safeguarding layers allowed a local loss of containment to escalate. In the Sulphur incident, key monitoring elements such as CCTV, gas detection, and alarms were offline, with notification coming from external responders. An effective safety instrumented function (SIF) applies the fail-safe principle to trigger emergency shutdown (EST). But here, the absence of validated inputs created diagnostic gap, delaying recognition and isolation.
First, if degradation makes leaks more likely, the most common idea is to harden the hardware at its weak points. O-rings and elastomers used must qualify for rapid gas decompression and supercritical CO2, with polytetrafluoroethylene or other non-elastomeric sealing where possible, while simultaneously complying with the PHMSA regulations for plants nearby residential areas. We should focus on inspection on elbows, low points, and small bore connections where corrosion and pitching occurs by using stainless steels such as 316L, Duplex 2205, Super Duplex 2507, and nickel alloys, plus certified internal linings such as epoxy-based phenolic coatings, glass-fake reinforced epoxy, and TTFE liners for highly corrosive chemicals.
Second, because a small leak becomes big when flow continues, mass flow needs to be cut fast. We will install dual pressure transmitters per segment and run a rate of pressure drop algorithm that fires an emergency shutdown in about 10 seconds when decay matches a credible leak. Where hydraulics allow, ball spacing can be shortened so any discharge volume is limited. Third, since carbon dioxide pools low, put infrared point detectors near ground level where the plume will collect and use open path infrared across bays to attach anything the points miss. Low-mounted infrared carbon dioxide detectors provide early warning because carbon dioxide is heavier than air and tends to cool near the ground. A compact meteorological unit can also be installed to stream wind speed, direction, and atmospheric stability index such as the Pascal-Gifford class to the alarm logic.
Next, put someone on duty 24/7 with a clear response, time target. Publish 2 metrics and live by time to detect, time to isolate. And train the nearby community little and often. A short weekly refresher, a monthly valve drill, and quarterly end-to-end rehearsal to prove detectors, logic, communications, and valves still work together. We can also extend the safety net to community with outdoor sirens and opt-in SMS app notifications so neighbors are alerted the moment of CO2 detectors, alarm, or any emergency shutdowns triggers.